I'm a PhD student in the fluid dynamics research group in mechanical engineering, and I'm going to sort of talk about the paper I've just submitted for review on some scaling models for hydrogen flames. So, firstly, what is the sort of motivation and background for this study? So, why do we care about lean hydrogen combustion? Why does this lead to, and what is thermodiffusive instability? This is the combustion instability we observe, and what kind of factors affect the amount of instability we get. This sort of naturally leads us towards a scaling model. So I'll overview the aims and methodology of what we did, how we analyzed the direct numerical simulation database. This is a numerical study, and the particular functions we got at the very end. So why lean hydrogen combustion? So when we burn fuel, we have this sort of three-way trade-off between efficiency, emissions, and stability. So hydrogen burns very efficiently, so you don't need much of it, and you'll get a lot of energy out of it. Obviously, we have great emissions. It's carbon-free, so we don't have any carbon emissions, and we also would like to reduce, for example, our NOx emissions. So to reduce our NOx emissions, we reduce the fuel-to-air ratio. And what this does is this reduces our exhaust temperatures, our adiabatic flame temperatures, and this prevents the production of NOx. However, when we burn lean, so when we burn with this low fuel-air ratio, this introduces combustion instabilities, specifically thermodiffusive instabilities. So what is thermodiffusive instability? So because hydrogen is such a small molecule, it moves very rapidly, it diffuses very rapidly. And as a result, we have this imbalance of diffusion across a flame. So a flame can be seen as, on one side, having cold, fresh gases of a high density, and on the other side of the flame being hot, burnt gases, so with a lower density. And what we have across the flame is we have heat diffusing from the hot side to the cold side, and we have fuel diffusing from the cold side where the fuel is to the hot side. And if these if the diffusion coefficients are imbalanced, so this is quantified by the Lewis number, which is the ratio between the diffusion coefficients, we can get these sort of cells that burn much hotter. So these cusps here will burn, the fuel will rush into these cusps. This will increase the reactions, and therefore we get the flame moves faster in these areas and it burns hotter in these areas. This is what happens on sort of a local scale. It also happens in these areas here where we have the sort of cusp going the other way. The hydrogen just diffuses out and we get local extinction, so no burning happens in these kind of regions. In terms of what it physically looks like, these are experiments done in Aachen University. And there you can see here, so this bottom picture is just with methane, which has a Lewis number of 1, which means that the diffusion coefficient of methane is approximately similar to that of the heat. So it's roughly balanced, and you get a very smooth looking flame. That's sort of in a flame kernel, which is this kind of explosion outwards, is very smooth. Whereas in hydrogen, you get a highly wrinkled flame, and this causes it to burn much faster and much more sort of irregularly. In terms of locally, as well as moving faster, it also is thinner. So although we view a flame as being infinitely thin and like a surface, it does have a characteristic thickness, usually on the order of, say, a few hundred microns. And what this instability does, as well as accelerates the flame, is it makes it go faster. As well as it accelerating the flame, it makes it go thinner as well. So what factors affect this amount of instability? So obviously the Lewis number, as we've said, if the Lewis number is lower, that means we're going to have more instability. But also the sort of global conditions. So the fuel-to-air ratio, the equivalence ratio, phi in this case, the lower that is, generally the diffusion is dominated by the fuel diffusion, and you get stronger instability. Also, the temperature of the gases before they burn affects the level of instability, and the pressure of the combustor. So here we can see some pictures. So these are temperature plots. So the blue is like cold, and red is the standard exhaust temperature, and pink means we've got like hot spots occurring. So here is our sort of base case we used. We had a fuel-to-air ratio of 0.4, 300 Kelvin premixed gas, atmospheric pressures. and we see this sort of level of wrinkling occurring. If we increase the pressure, we can see we get more wrinkles, we get hotter spots, the flame moves faster. If we decrease the equivalence ratio, again, we see more wrinkling, moves faster. However, if we increase the temperature, we see that the flame sort of is quite flat. And in sort of in a methane flame, you generally don't get these kind of exceptionally wrinkled flames. You just get red in the sort of post flame, no pink regions, and usually maybe one sort of big cusp or something like that. So experimentally, we've seen that this stability is dependent on the Lewis numbers of the fuel, the oxidizer, the fuel to air ratio, the unburnt temperature of the fuel air mixture, and the pressure of the system. Theory tells us that this stability is dependent on the Lewis numbers, the fuel to air ratio, the Zell division of beta, which is essentially a measure of the activation energy, and this is a function of temperature and pressure and equivalence ratio, so it's a function of all of these, and sigma, which is the density ratio. So I said on this side we have a rather high density, and on the other side we have a low density. So the ratio of these two densities, this density ratio, dictates how unstable the flame is. So we can get this this stability parameter omega 2 from inexpensive one-dimensional simulations. So these simulations here are two-dimensional. These are not 3D simulations. These are 2D simulations, but we can also perform 1D simulations. So to compare computational cost, a one-dimensional simulation can be performed in under a minute in Python. It's extremely easy. There's a Python library used called Cantera, which we can script out a flame in 1D very, very easily. In 2D, I can run this on, say, my workstation at university in, say, a day. In 3D, we have to run on the university's HPC system rocket for multiple days to get meaningful data. So we wanted to evaluate these conditions in lots of different conditions. And we wanted to compare this stability parameter omega 2 that we can calculate from just a one-dimensional simulation. So as you can see here, we have, for this flame, omega 2 positive, we get completely like chaotic, lots of cells, hotspots. Approximately 0, we have a flame that's on the point of being unstable. This is the same one as earlier. And this is actually a methane flame. So we just get a very stable looking flame, just red, no pink areas. So this is kind of one of the big takeaways is how can we, so is calculating this in 1D. So we have a contour here for different temperatures. And then on the axes, we have equivalence ratio on the Y and pressure on the X in a log-log scale. And as you can see, we kind of have this ridge happening. So we have a peak surface where we expect the most instability to occur. So it's not, despite earlier, we had the slightly misleading idea that, we increase temperature, we monotonically decrease in instability, we increase pressure, we monotonically increase in instability, we decrease equivalence ratio, we monotonically increase in instability. That's not quite the case when we reach these sort of more extreme conditions. And so we found a function for this ridge in this space where we expect the most instability to occur. So our scaling model was to basically take these omega 2 values and calculate the freely propagating length and speed changes. And what we mean by that is, I mentioned earlier, that this instability causes the flame to be thinner and faster. And we basically want to say, okay, how much thinner and faster? So we can calculate a thickness from one-dimensional calculations, and we can calculate speed from one-dimensional calculations. But because diffusion is by nature a multi-dimensional effect, we can only see this change in 2 or 3 dimensions. So we want to see how it scales from one-dimensional simulations, which are extremely cheap, to 2D simulations. So we had 40 different conditions in a range in the pressure, temperature, and equivalence ratio space. And we let the flame, we didn't perturb the velocity field in any way. We let sort of flame do its own thing. The range of physical conditions, 1 to 24 atmospheres, 300 to 650 Kelvin, and a fuel to air ratio of 0.2 to 0.4. If you go above 0.4, we're sort of entering the region where actually you don't see much instability. We also use a complex chemistry mechanism with 9 species and 29 reactions. So one thing we have to do when we're analyzing these flame flames is pick a flame surface. So I said earlier that we consider a flame to be infinitely thin, and then I also said that's not actually true in sort of in the real world. When we're modeling it, we assume to be infinitely thin. But as a result, when we're analyzing these flames, we have to pick a flame surface. And how do we do that? So we want to align it with the fuel consumption rate. So this is the fuel consumption rate on the left. As you can see in these cusp regions, we're getting far more fuel consumption than we have these areas of local extinction in the opposite cusps. And what we found was that actually temperature, which is typically used, and say if you pick a contour of 1,000 Kelvin through this flame, that is a very sort of standard way of defining a flame surface. However, doing this in these kinds of flames, because of these local extinctions, we ended up with, say, 1,000 Kelvin ballooning it way into the post flame, and this would massively overestimate the flame surface. You can see this on the right as well. We have this flame surface sort of balloons into the post flame, as we call it. So instead, we define our surface based on a value of fuel mass fraction. So I mean, so how much, so say a fuel mass fraction of 0.1 or something, and we found that this aligns far more closely with the flames with the fuel consumption rate. This allowed us to take statistics from the flame more accurately. So in particular, the actual scaling functions, we found that actually, so I talked about this ridge earlier. I'll just quickly shoot back to it. This ridge, we found that simulations we performed above the ridge scaled differently to those below the ridge. So the ones below the ridge, to reasons which we are still trying to figure out, seem to be a bit more extreme in their response to the conditions. So the actual functions we have on these, for the red points, we had a linear function for flame speed. So SF or SL means basically the freely propagating flame speed, so the flame speed in 2D versus divided by the flame speed in 1D. So this is so red indicates below the ridge, and black indicates above this ridge. So we see an exponential behavior above the ridge and a linear behavior below the ridge. Similarly, we found in the inverse scaling for thickness. So we found that the flame gets thinner, and that is exponentially thinner in above the ridge, and sort of inversely, well, linearly, but hence inversely thinner below the ridge, which we've thought is quite interesting. We're currently trying to investigate. So in conclusion, we've sort of discussed the need for lean hydrogen combustion. Personally, my work is I'm being sponsored by a company that develop engines for rockets. So that's the particular application for my research. But obviously, this research is exceptionally useful for any kind of hydrogen combustion, how we can predict the instability, the amount of flame instability we will expect to see, given the sort of the overall conditions that we're burning under. We've talked about the origin and effects of thermodiffusive instability. We found this, we called it a ridge function, which is actually a surface in the 3D space. Then we conducted a broad range of two-dimensional simulations of these unstable, lean, premixed hydrogen flames, and we have these functions that we found from this study. And so the future work that we're going to be doing from this is we're going to be testing the validity of this in 3D. So we expect a similar behavior, but potentially different constants. The contours we generated, due to them being from 1D, they will be identical. But we expect, for example, these numbers to be potentially slightly different, and probably a stronger response due to, adding another dimension another dimension where diffusion can take place. So we're expecting to see an even stronger response in 3D. And we're also wanting to investigate the interaction of these instabilities in this kind of setting with turbulence. So instead of just having a completely laminar fluid flow through the domain, we're going to introduce some kind of homogeneous isotropic turbulence to the numerical experiments. Even further, we're potentially also going to look at partial premixing. So instead of having a nice uniform distribution of hydrogen throughout the fuel air mixture, a more realistic way of burning is obviously that we have like blobs of fluid. You don't expect to have a perfectly pre-mixed. It's a very sort of hypothetical situation that we actually burn in. So we far more expect to see like blobs of fluid, and we're also investigating how that affects the level of flame instability. That's everything from me. So if anyone has any questions.
Thank you very much, Thomas. That was brilliant. Unfortunately I cut out halfway through, so hopefully that went all fine and no one noticed that. Are there any questions in the chat for Thomas? Seems to me like everyone wants to go to lunch.
Well, if no one has any question, I'd like to ask. Thank you for an interesting presentation, Thomas. Well, this is a little bit of a naive question, but do you think in the long run that hydrogen flame could ever replace and could ever be made so stable and safe that it replaces our ever so popular log burning fires in our homes? So we stop burning carbons just for the beauty of it.
I don't think a log burning fire in a home. I think the main sort of applications of these kind of hydrogen combustion is probably it's sort of in much larger applications than in the home. So cars, obviously, I work with people who make rockets, or probably I don't know about planes, but boats, for example, is another one that people are very keen on moving to hydrogen, but probably not in the home.
You think it wouldn't be safe yet? I mean, as I've seen some research of being funded to produce a flame that's equally nice as carbon burning flame, just that is zero emissions. So you think that hydrogen wouldn't be good for that?
I mean, you get some extraordinarily pretty looking flames in terms of experimentally as well. So potentially, even more so as we've seen than carbon flames. So potentially.